Okay, because it's going to continue in the theme today, and I should again, it's nearly 5 past, so I'll make a start. I'm only, as usual, waffling anyway. But it is very important to have, and again, maybe you kind of think that that's, if you particularly, I know we've got a lot of very brilliant maths and physics students this year, and I think, I taught you maths last year, and I know most of you are very good at maths. But it's nice to have both an intuitive and a mathematical grasp of what's going on. I think for a physicist, it's very important to have both. You can't just say, oh, well, now I know the Maxwell equations, I'm so clever at maths I can derive everything about electricity and magnetism. Most real-life situations are too difficult for that to be true. And so you need a kind of intuitive grasp. And what I'm hoping to do this week is make sure everybody's got a good intuitive grasp, because we've got to relate, like we did yesterday, we related the Gauss flux law, which is an integral law. It's got integral signs in it. It's the integral of the surface component of the electric field is equal to the volume integral of its divergence. That is an integral law, but we were able, using Gauss's theorem, to extract from it the differential law. And we're going to be using both throughout the course. And it's very important that you kind of get fluency in translating between the two. For example, in optics, we'll use only the differential forms. And you certainly can't understand the unification theory without the differential forms. But for many practical applications, you have to use the integral form and work out the total flux coming out of a surface. So you need to be confident with both. And I hope after Wednesday's lecture that you're confident that Coulomb's law and Gauss's flux law and this new looking law, del dot E is rho over epsilon naught, are equivalent to each other. So now we're going to move on straight away. As I said, you can solve some more sophisticated boundary type volumes in electrostatics using Poisson's equation. And again, I mentioned, I just sort of like scribble it, it's not really particularly part of this lecture, because it's a conservative field. And again, very important point I'm coming to today, it's only a conservative field because it's got a zero curl, and this is only an approximation to the full set of Maxwell equations. So it's only true in electrostatics that we can define a potential. But in electrostatics, we can always write that the electric field is the gradient of potential. I'd also like to thank one of the students, Luke, who pointed out to me at the end that when I was doing the line integral of an electric field around a closed loop, or indeed any vector field around a closed loop, or indeed any integral that doesn't have to be closed, I used d small s as a line, as an element going along a path, and Kieran used dl for the same line element. So, of course, I always welcome comments like that, and apparently that caused a small degree of confusion. But it's just, again, it's a change. I think L's, particularly with I've already mentioned my rho and my E, and, so if we've got rho and then we've got a unit vector like that, and I've got an L, I don't want to cause, well, obviously as a physics lecturer, I'll cause lots of confusion, but I want to minimise it. So that was just, if you like, a trivial point. Now, when we come on to the next subject, sorry, I forgot to make my point there. This is like, really well organised stuff. Obviously, if E is minus del phi, and then del dot E is equal to rho over epsilon naught, becomes del squared phi is minus rho over epsilon naught. And if you like, again, this is the, excuse the kind of slightly flippant language, this is, the Aston Martin, the Lamborghini way of solving electrostatic problems. And I want to emphasise why these differential forms are so important is they're true at every point in space. And as far as we know, this law is true at every point in the universe. So it's extremely powerful, whereas the overall integral laws are not as powerful. And indeed, as I say, unless we get on top of the differential forms, we're not going to get on top of the unification theory, which is, the most fun and interesting part of the course. So we're going to go immediately now to what's called magnetostatics. So, typical start to a physics lecture, there is no such thing as a static magnetic situation. So you might say, well, this is a bit of a silly title for a lecture, but I want to point out that charges have got to be in motion to make a magnetic field. We've got a static electric charge produces an electric field, and a current, this is the current density, I'll come back to this, a very important point in a minute, a current produces a magnetic field. So you can't really say that there's a static magnetic situation. So it's a, let's say because, let's put this up a bit, there must be currents to get a magnetic field. This is, again, I'm writing this out in full. It's, it's in the VLE notes, but it's, it's worth writing down once, twice, three times, to emphasise that this is a particular approximation. And what kind of approximation is it? It's a, so magnetostatics, the title of the lecture, refers, I'll get this exactly right, to a special kind of dynamic situation. And it refers to this type of situation only, which is with large numbers of charges in motion. Very wordy start, I'm afraid, but we'll get onto some, if you're eager to hit some equations, don't worry, we've got plenty coming up. With large numbers of charges in motion and also which we can approximate, maybe underline approximate, whole of this study. Electrostatics is, again, it's completely approximate, the whole subject. It's only valid when dB by dt is naught, and likewise this situation is only valid when dE by dt is naught. It's already an approximation, and this current density we can approximate by a steady flow of charge. In other words, the charges are in motion, but the current, more precisely the current density, is not changing as a function of time. So exactly, if we've got the simplest situation where, like, put a battery across a resistor, couldn't get easier than that, and then we have a step, when we first switch it on and the current's building up, this doesn't apply. When we switch it off and the current's decaying, this doesn't apply. It's just the situation where we've reached some steady state where we've just got a current density that's constant with respect to time. Now, again, this week is very largely to root my course in Kieran's course. And in fact, we've covered the first half of Kieran's course basically on Wednesday, and we're going to cover quite a lot of it today. But to move forward to these new ways of the equations. So one of the big differences is Kieran used a scalar current I. And that's what we learn at school, V equals IR. It's probably one of the first equations we all learn in electricity, Ohm's law. And I there is just a scalar quantity. It's so many amps of flow. But I am going to start by analysing fine wires next week. But this is a more general concept. But I'm going to use this because I want to relate. Kieran hasn't yet studied with you, like this current density would apply, for example, to a proton beam in space. It wouldn't apply to one single proton in space. It's large numbers making a steady flow. It would apply, however, to the beams used at CERN. So if you have a beam of protons going round in an accelerator, then you've got a steady flow. So this is more general than fine wires, but I'm going to use it first to analyse the fields around fine wires. Of course, these equations apply in all sorts of circumstances. We relate the current density, and did Kieran define this at all? Did he use a current density in his course or just current? Usually in sort of elementary electromagnetism, it's only written in terms of the current, but we relate the current density, J, and note, first of all, this is a vector quantity, and it is in amps per square metre. To the total current, I, this is the total current I in the, especially if you're close up with that microphone, that probably didn't come out very well. I'll try and avoid that. The total current I in the wire, by starting off with a very, very easy equation indeed. Let's just move these up a bit so we've got all this side available at the same time. J dV is equal to I ds. And again, this is the small s, which is a displacement along the wire, and I'll make that equation 3-1. And this is illustrated in figure 16 of the course handout. So let's pop that one up. I should say I've reorganised the lectures very slightly compared with the VLE. Today's lecture is going to be a mixture of what's on the lecture notes in the VLE of lectures 3 and 5. There are 4 lectures, lectures 3 to 6. All of next week we're doing magnetostatics. And I think, obviously when you give the course 2 or 3 times, you can think that perhaps of a slightly more logical presentation. And I like to think, I'm improving the course as I go along. And, you're in the middle of undergraduate course. I'm sure you'll be able to work out how this links up with the VLE. But this is about half of lecture 3 and half of lecture 5 on the VLE notes. So again, I'm sorry, when I copied it, I'm going to use A for cross-sectional area throughout. So you might want to correct in your handouts that this Feynman here used big S for a surface, but he also uses little s for this line displacement along the wire. Again, that's what Kieran called dl. So I think A is much better to use for area. This is a displacement along the wire. And again, I copied this from a book, so it was originally in bold type. The current density is, of course, a vector quantity, and a directed line element along the wire is a vector quantity. And clearly, if I've got J amps per square metre going along the wire in an infinitesimal volume dV, again, it's like, the most extremely obvious dimensional analysis. J is in amps per square metre and dV is in metres cubed. This will clearly be equivalent to I ds. And note that the vector has sort of nipped over. In kind of elementary style, which doesn't fit so well with the Maxwell equations, you have a scalar current and then you consider some displacement ds along the wire. I'm always going to consider a current density, and that current density is just like that heat flow vector. Heat is telling you how many joules per square metre per second are flowing through, of heat energy are flowing through a unit area. The current density is telling you how many coulombs per square metre per second are flowing through the area. And of course, a coulomb per second flow of charge is an amp. So please note, when this is right at the beginning, that the current density J is a vector quantity and I is a scalar. And of course, you've got to have a vector on one side and a vector on another. It's the displacement that carries the vector quantity in the way that it was presented to you in EM1, and this is the way we're going to use it in EMO. And of course, finally, trivially, if you're in we're going to use, as I say, J is better because we could have a beam of protons that's going around in space. It could be curving, you know, and then we would like to be able to describe that in electromagnetism. But if we've just got a fine wire, well, obviously the magnitude of the current density in amps per square metre times the cross-sectional area of the wire is just equal to the scalar current. So that, as they say, was the easy bit. So this one is illustrated in figure 16, and let's move these up a bit again. Note that I know it's a bit trivial at first, but note that the magnitude of J times the area is the scalar current. So we'll make that equation 3,2, where A is the area of the wire. So again, in your figure 16, that area has been written as surface S. So I'm putting this in to emphasise that this is that I'm changing over. So the crucial property of a magnetic field, and again, I get all my, like my bloopers out of the way at the beginning. So these are the two figures probably in the course that really need correcting up. Is in particular when I'm applying to magnetism. Again, I copied this from a book. And it'd be one of the things I emphasise today and throughout next week is you cannot express the magnetic field as the gradient of a scalar field. And so I'd like you to cross out this gradient of a scalar field and just put in some general vector field C. Now again, I did that little kind of show of hands at the beginning about whether people felt confident with the material in Maths 2. It seemed to be most people had some feeling of confidence. Again, we're going to be using line integrals a lot in the magnetism and indeed in the electromagnetism. So remember, if I've got my vector field C can be pointing at any old angle here, and I make some small vector displacement along, well, what I mean by the tangential component, this C subscript T means tangential component, will be C dot ds1 in this region, because remember the field is going to be varying from point to point, so this will be the value of the field at this point, and this is equivalent, as we studied last year, to projecting the vector field, looking at its tangential component, projecting it onto the path. So again, you've studied this before, but I'll make a bit of a quick note on it, which is that the crucial property of the vector field B is its circulation again, this comes from the old days of when these fields were first considered in, say, the context of, for example, flow of a liquid. And then this would literally, if this was a velocity field, then if this was a velocity field and we close the loop round, that would actually represent the flow of liquid going round. In other words, it's circulation. We still use circulation for magnetic field, even though nothing's actually really circulating. It's just a field that exists in space. But we still use the word, and it's defined by the integral. And again, I assume everyone's familiar with this, that the circle on the integral sign means we close the loop. The subscript gamma defines which loop in space, and it is, once you've defined the loop, B dot ds, where gamma, capital Greek gamma, represents the path. Again, you'll see different nomenclatures in different books. I hope you don't just read the Feynman lectures or assume that's the only way of looking at electromagnetism. And again, because I want to be unambiguously clear, ds is a directed line element on the path. And indeed, this is illustrated in figure 21 of the course handout. Note, don't, like I did, use del psi. This was illustrating a different, the book I took it from was illustrating a different point. So what I want to now, we've now defined what we mean by this integral, and we've defined what we mean by the current density, and we're now going to go to Ampere's law straight away. So Ampere, and we're now moving into the 19th century. Coulomb's law, I think, was 1777. And, of course, this was a massive advance. It was the first quantitative law to do with electricity, the inverse square law for static charges. The first discovery of the law for flowing currents was made by Ampere in 1820. And he discovered that. Now I'm going to write it in the more rigorous form, that the line integral of the magnetic field around any closed loop is equal to mu naught, this is the permeability of free space, times the surface integral of the normal component of the current density integrated over the area bounded by the loop gamma. So we'll make that 3. And again here, mu naught is the permeability of free space. Again, a lot of things in the first week will overlap with EM1, is the permeability of free space. And a subtle point here, and I hope this came out in your Maths 2 course, because it sounds at first that this isn't going to be that meaningful, but it is very useful for later on. And S is any surface. Doesn't have to be the flat surface bounded by the loop gamma. It's any surface bounded by the loop gamma. So equation 3 is the integral form of Ampere's law. So this is the law of steady currents flowing in fine wires. Now, I checked Kieran's notes, and the left-hand side of this equation you're entirely familiar with. The right-hand side, he wrote slightly differently, but once we've got equations 3.1 and 3.2, they're related pretty trivially, because the surface integral, let's just go back to figure 16. Inside the fine wire, the current is constant. So, and it's parallel to the displacement along the wire. We've just got a current flowing along the wire. So its normal component is precisely just the magnitude of J, and the integral, because it's constant everywhere across this area A, we have got that the magnitude of this is everywhere constant, it's everywhere parallel to this. So basically all we've got to do is take J dot N is the magnitude of J because they're parallel. The normal to this surface A is precisely along the wire. The current's precisely along the wire. So we've only got to J dot N is just the magnitude of J. And if we multiply it by the area, we get the current I. And this is the loop, and this is the current. Kieran called it the current threading the loop. So let's just write that explicitly, that the surface integral over J is just the total current I. And it's like, use Kieran's words, threading the loop gamma. So let's now just move this up a bit as well. We've got that the law becomes that the circulation of the magnetic field is equal to mu naught just times the total current. And exactly, Kieran described this as the total current threading the loop. However, if we want to move to more advanced way, this is, if you like, this of course is true for a fine wire, and this is there's nothing wrong with this equation, but I'd not just much rather, we've got to go over to thinking of this as the surface integral of the current density through the loop, as expressed in equation 3.3. So 3.4 is just happens to be a nice easy way if we're doing fine wires. Now, the integral form 3.3 is related to the differential form. This is, as I say, where we've got to go in the course is over to the differential form. The differential form, this is precisely the same law of physics, but expressed in differential rather than integral form, is del cross B is mu naught times the current density. That relationship is done by Stokes' theorem. And Stokes' theorem is, let's put, sorry, it's got a bit crowded here, but I don't want to use a separate board. See figures 22 to 25 of the course handout. As I say, I'm now jumping on to lecture 5, but I wanted this week to get on top of really these two. We're going to be using Gauss's theorem and Stokes' theorem again and again. So again, what I would advise you now, and it's up to you, is maybe specifically not to take notes for the next 10 minutes, precisely because this is all on the VLE anyway. And there's I mentioned on the VLE, I've given about a 45-minute talk on Gauss's theorem, about a 45-minute talk on Stokes' theorem. And for those of you who put a hand up, so I was a bit shaky on maths too, strongly recommend you to use these semi-intuitive proofs. And I'm just going to run through it in the next few minutes. So, what is Stokes' theorem? Well, Stokes' theorem is telling us that, well, first of all, let me just write Stokes' theorem down. Let's just kind of, if you like, see where we're going with it. And I think I would like to, again, write this down in terms of the general vector field. Let me just move this up a sec. So, excuse me, it's the early term chalk dust. Make sure I want it to be exactly the same because it's so important. I want this to be exactly the same as in my notes. Switch this off for a second. So Stokes' theorem states, and again I'll put it in words and in the equation. Again, because this is a general mathematical theorem, I'm going to write it as C. It's not just true for magnetism or electricity or heat flow, or this is a general theorem of vector fields, that line integral of any vector field, in other words, the circulation of any vector field, is equal to the surface integral of the curl of the same vector field. In other words, we integrate its normal component over the surface. And again, that has been proved to you, pure maths, and definitely a true mathematical theorem. So then this is an integral. If we have the circulation of C around a closed loop, then the curl, the normal component of the curl coming out through the loop, integrated over that surface, is identical to this side of the equation. And figure 22 shows that. Now, the idea of figure, as I say, it's up to you if you want to take notes, but it doesn't make any sense like that. Let's get this out of the way. This is all there on the VLE, so I'd advise you to just like go through the proof with me for 10 minutes. So we've got an outer loop, and I know the circulation of the field around that loop is this line integral. Well, now what happens if I make a cut across the loop? And by an incredible coincidence, I've got a loop and a pair of scissors. So we're now from the, this is like Blue Peter's guide to the Maxwell equations. But so let's say I've got a field that's circulating around. Okay, here we go. I'll draw the circulation like that. There we go. How does that? No, probably doesn't show up very well, but there we go. I now literally make a cut across this loop. Yeah. And now I consider the circulation around this loop. And you'll notice that when I'm making the circular, I'll do it this way around, I make the circulation around this loop, the line element along this cut surface here is pointing downwards, yeah? If I take the circulation always, as shown there, counterclockwise, the line element as I'm going down this element of the loop, the displacement is identically down, yeah? However, remember, the loop, it's going around this way. As I go across this cut element of the loop, the displacement, remember, I've got to keep going anti-clockwise in both of these loops to be consistent. You'll see the displacement element is exactly equal and opposite across the cut. And that's what's illustrated in this diagram here. So if I consider the circulation around gamma 1, well, that's equal to, maybe use a different colour here, that's equal to the circulation around this part of the loop, called gamma A, plus the circulation, the circulation is only when I've done the complete circuit. The line integral around is composed of two parts, this one gamma A, and this one, which is gamma AB. AB because it's this cross thing here, and DS1 going around this side of the cut loop is definitely in that direction. I now consider the circulation around gamma 2, yeah? And that consists of this outer part of the loop, start here, go round to here, plus this integral along here, gamma AB of C dot ds2. But it's intuitively obvious, just by literally cutting a piece of paper, you don't have to do more than that, that ds1 is equal and opposite to ds2. So when I add the circulation around gamma 1 to the circulation around gamma 2, I get four pieces, this piece, this piece, this piece, and this piece. But because ds1 is equal to minus ds2, these are equal and opposite. So all that I'm left with, the bit that doesn't cancel out, is the circulation around gamma B and the circulation around gamma A. But that's just the circulation around the original loop. So in other words, I can cut across, and if we now add it, the sum of the circulations is just equal to the original line integral. So I can cut, and if you've got your head round that, it's perfectly, just like, if you get your head round the chopped potato image, once you've chopped it once, it's clear you can use the same argument again and again. And so likewise, I can now, well, I've now got a subloop. Well, here we go. And I now chop it down in this way. Well, the circulation around this loop here is obviously, by the same argument, equal to the circulation around this bit plus the circulation around that bit. This line element cancels that line element. It's the same as that circulation. I now put it back together. It's the same as the original circulation. So I can cut and cut and cut And again, I got a very fast pair of scissors. I cut it into some infinitesimal squares. Yep. So I keep subdividing, and I always will get, any time, it doesn't matter where, you can consider anyone here, for example, let's take that point arbitrarily. Well, that circulation is going downwards from this cell, but from the adjacent cell, it's going upwards, so it cancels. And so the circulation, all I've got to do is work out the circulation around a small square, and there are all the pieces up. It must give me the original circulation. Couldn't be otherwise. So, and again, I've emphasised this. This will be important when we come to the Ampere-Maxwell equation. Although, of course, the view graph's flat, I don't have a kind of like, curved view graph. A curved surface can still be divided up into infinitesimal squares that are locally flat. So, therefore, the argument will apply. So, it's still, now, it reduces everything to working out the circulation around a small square. And the circulation around a small square, well, that's pretty easy. There's only 4 pieces. Again, of course, this has been taken from a book. This is a vector field. I'll just go first. Let's consider I go along leg 1. Well, and again, this is a slightly intuitive hand-waving proof, like my Gauss's theorem, when you've done it rigorously. But the vector field has got some value, and let's guess that the value, this is so small that I can just say is the projection Cx on this axis times the displacement. That is, by definition, I've projected my vector field onto the x-axis. In other words, I've projected out its x component. So the first part of my line integral is the x component along 1 times the displacement. Now, likewise, on this leg here, I project the normal component onto this direction is just the y component. So the next leg of this circulation is cy times delta y, where delta y is the distance I go here. Now be careful, in leg 1, our ds was going that way. In leg 2, we're going along the minus x-axis, so it's minus the value. And again here, the vector field will look like this. We project its component, but now onto minus x. Similarly, along here, the vector field, remember it's a continuous field, so it's only going to vary very, very, very slightly in this little square. So all this vector field is all going to be roughly the same magnitude and direction. And then the last piece, remember now I'm going down the minus y-axis, is this piece. Well, now let's join up this piece. And again, at first you think, oh, they're just going to cancel out. The vector field's almost constant over a tiny square. But the x component here is slightly different in leg 3 to 1. But now it's varying in the y direction. We've got to consider how rapidly is the x component of the field varying as we've gone across delta y. And then we multiply by delta y. So this is the underlined piece here. There's a slight difference that Cx and the upper leg is equal to Cx1 plus a little bit, depending on how the x component of the field is varying in the y direction. So when I subtract off Cx3 from Cx1, the lead terms cancel, but there's this little piece left, minus dCx by dy times delta x times delta y. And now I can apply, if you get your head around that, well, obviously I apply the same argument to these 2 legs, but in these 2 legs, it's the y component of the field is varying in the x direction. The y component here is slightly different to the y component here, and therefore I get a very similar term, dcy by dx times delta x delta y. So the total circulation around this small loop is dcy by dx minus dcx by dy times delta x delta y. And now we can clearly identify this with the normal component of the curl. Precisely what, we all know how to define the curl, that it's the I, j, k, d by dx, d by dy, d by dz, cx, cy, cz. its y component is precisely d by dx of cy minus d by dy of cx. Precisely this creature here. So we can see that this is the x component of the curl, and it's the z component of the curl, and this is clearly the area of the element in the plane. So again, I say it's a non-rigorous proof. I've just done it in the xy plane, but we've done vectors. We can always choose to reorient our axes if we need to. This is clearly the area, and this is clearly the normal component. I mean, for the xy plane, which we chose, we get the z component of the curl. If I'd chosen a different plane, I would have got a different component. But in general, this is the normal component of the curl. And instead now, when I take the limit that these little squares become infinitesimal, this becomes dx dy, in other words, becomes dA. And instead of adding up all the little squares, I have to integrate over all the little infinitesimal squares, precisely as illustrated in figure 25. So the circulation of C, remember we subdivided it, we've worked out that that must be equal to the normal component of the curl. When we generalise, it came out in that little calculation as the z-axis, the normal component times the area element. So when I go round this loop, instead of adding up all these little squares, I integrate over the area, and I therefore get the integral, surface integral, over the area of the normal component of the curl. It could not be otherwise. So that's my intuitive sort of 10-minute proof of Stokes' theorem. So this one, as I say, is illustrated, and we'll be using it again and again, just like we'll use Gauss's theorem again and again. So now we've got Stokes' theorem. So this, I should say too, I've cribbed this proof from, I'm not ashamed of having taken things from the Feynman lectures. He was one of the greatest physicists and greatest lecturers of the 20th century, so copying his style of electromagnetism is, I don't think, the worst thing a lecturer could do. This is a page of the Feynman lectures, and you can see where my diagrams came from. So no problem if you want to revise it straight, if you like, from the horse's mouth. I should say too that somehow to our minds, I don't know why, the idea of divergence at a point is a bit more intuitive. And people have, and this is why I've spent a bit more time on Stokes' theorem than Gauss's theorem. I've marked electromagnetism and optics exams for 2 or 3 years, so I know people have more difficulty with magnetism than electricity. And I think be reassured, if you find this Stokes' theorem difficult, you're in good company. So did James Clerk Maxwell. And this is a paper from his in 1861, earlier in the year. This is one of the greatest physicists of all time at his peak, saying, you won't be able to read, I have found great difficulty in conceiving of the existence of vortices in a medium revolving in the same direction about parallel axes. See, he's kind of like really worried about this aspect, is that when you take these squares to be actually infinitesimal, again, let's take this example square here, well, it's flowing in this direction in this cell and in this direction in the adjacent cell. So the same point in space is circulating, is moving in opposite directions. And of course, that, get your head around that. Maxwell said the contiguous portions of consecutive vortices must be moving in opposite directions, and it is difficult to understand how the motion of one part of the medium can coexist with and even produce an opposite motion of a part in contact with it. This ain't easy. I didn't say electromagnetism was going to be easy, but he used a kind of mechanical conception that has now dropped out of favour. We just particularly now say, oh, it's a vector field and its circulation is a well-defined mathematical quantity, the curl is a well-defined mathematical quantity, it works. Let's not worry about these problems. There's no medium at all. Electromagnetic waves propagate in a vacuum. We dispense with these kind of mechanical models. And there's a certain irony that Maxwell actually derived his great theory in terms of a mechanical model that we've now entirely discarded, because the mechanical model seems to give rise to these almost impossible ideas. So we just accept that Stokes' theorem is true. So that's... But we're now in the position to reformulate the law. So let me bring this one back down just for a minute. So this is the integral form. And again, I want you to get away from just thinking of this as some global current I. This is the integral form of the equation. And now this is a general equation. So clearly, the line integral of B dot ds is equal to the surface integral of the curl of B, normal component, integrated over the area. And to stress, if I write it as equation 5(7), all that I've done is said, well, B's a vector field. And if it's a vector field, and that's a general theorem of vector fields, then it's true for the magnetic field. And so again, now, the left-hand side of this equation is identical to the left-hand side of this equation. Therefore, the right-hand sides of these two equations are equal to each other. So again, this equation 5(7), that's pure maths. Yep. There's no physics in that equation. The physics, this is the physics. This relates the magnetic field to the current density. That's the physics. That's the kind of thing you measure with a Hall probe. That is really the physics. That is experimentally true. It took a brilliant piece of abstraction by Ampere to frame it in this way, but it is based on experimental fact. Therefore, I can say that the right-hand side of this equation, which is the surface integral of the curl of B, normal component over the area, is equal to, well, it's got to be equal to the right-hand side of this equation, which is that it's equal, therefore, to the surface integral, mu naught, times the surface integral of J dot N dA. Similar kind of argument to the one we used yesterday with Gauss's theorem. Well, if this surface integral over any arbitrary surface is equal to this surface integral over any arbitrary surface, then the integrands themselves must always be equal. Again, I won't make this argument. I'll take out this intermediate step in future, but then this thing here has got to be this thing here. The integrands, if the normal component of this thing integrated over the area is always equal to the normal component of this thing, normal component integrated over the area, they've got to be the same vector. Don't forget there's also this scalar on this side of the equation. Therefore, let's say it explicitly, if, again, I'll leave out this intermediate step, but in week one we definitely need it. If the integrals over any arbitrary surface are equal, let's move this up a bit. If the integrals, and that one maybe, if the integrals over any arbitrary surface are equal, the integrands are equal. And for the integral, if this field's normal component integrated over the surface is the same as this one, then allowing for the scalar mu naught, which we could of course pop inside the integral sign, it's a universal constant, so I can put it under the integral sign if I like. If you want to make it look even more kind of obvious, this thing here has got to equal this thing here, Therefore, the curl of B is mu naught J. So this is precisely what I wanted to cover in this lecture. So we've got a couple of minutes. We've got to the point where what we've done this week, we haven't done much more than simply reformulate stuff that you've studied so far. I would say we are going to, don't worry, we're going to get onto some completely new physics later on. But this is all that we've done, really. Let me just use the projector again for a second. Is that you've already studied Gauss's flux law of electrostatics, and you've already studied Ampere's law. Now, all that we've done this week, really, is to say that we can summarise that in these two pairs of equations. And these, as I say, are differential equations, are true at every point in space within the static approximation. Remember, and we'll come to this, this Ampere's law is actually not a general law. It's only true in this pseudo-static situation of steady charges flowing around. So far, we have just reformulated. This is, if you like, the advanced way of looking at Gauss's law of electrostatics. This is the advanced way of looking at Ampere's law of steady currents. We've just rephrased them using Gauss's theorem and Stokes' theorem as differential laws true at each point in space. Now, just one quick word. Of course, we've not got far enough into magnetism yet to do coursework. I'm going to set two problems this week. One of them is on the general form of the Maxwell equations, and it is kind of, by your standards, if you use a cricket analogy, it's slow underarm bowling. It's more or less saying what are the meanings of the symbols in the Maxwell equations. And incidentally, you might think it's trivial because I've asked you to say, write out what del dot E is explicitly. And when we write, I'm calling these the Maxwell equations, but Maxwell never wrote them in that way. Maxwell always wrote dEx by dx plus dEy by dy plus dEz by dz is equal to rho over epsilon naught. That's much more strictly the first Maxwell equation in the sense of the way he wrote it down. And sometimes of course, it saves chalk, it saves time to write it as the divergence of E, but don't feel that there's something naff or wrong about writing all the components out explicitly. And often when you solve a real problem, you've got to re-expand it out anyway. So and likewise, he wrote each component of the curl explicitly. There's nothing wrong with doing that. That's perfectly okay. Maxwell himself did it. The second problem is on electrostatics, and as it's 5-2, I'll maybe give you a hint on that one next week. It's also quite easy, I hope. Okay, next week we move a bit further along the line. Last chance hotel for handouts. I won't bring them along next week. So please, if you need a handout, collect it now.